space friend. Today's project involves using an accelerometer to maintain the right orientation of our spaceship. We'll use one with a piezo buzzer to provide audible data to help us with navigation and course corrections. Accelerometers can detect the magnitude and direction of acceleration. This is how smartphones and laptops can detect when a device is picked up or falling. The one I'm using today is the ADXL345. It can work with either SPI or I2C communication. It has 10 pins, but not all of them have to be used. The pins are VCC, which connects to a 5-volt power source, 3.3V, which connects to the 3.3-volt power source, ground, chip select for SPI communication, INT1, which is hardware interrupt pin 1, INT2, which is hardware interrupt pin 2, SDO for the serial data output pin, which doubles as the MISO pin for SPI communication, SDA for I2C communication, which doubles as the MOSI pin for SPI, and SCL for I2C communication, which doubles as the clock pin for SPI. Two common units of acceleration are meters per second squared and Gs. 1G is the rate of acceleration of gravity. The ADXL345 outputs separate acceleration measurements for each axis, X, Y, and Z. These refer to different directions in three-dimensional space where the device can measure acceleration. The x-axis represents a horizontal direction, usually from left to right or right to left. In most cases, it's the side-to-side movement. The y-axis represents a vertical direction, usually top to bottom or bottom to top. It's associated with the up and down movement. The z-axis represents a depth or front to back direction, typically coming towards you or moving away from you. It's commonly related to forward-backward or front-back movements. In an accelerometer, these axes help determine the direction and the intensity of the force acting on the device. For instance, when you tilt the accelerometer in a certain direction, it measures the gravitational force along that axis, providing information about the device's orientation or movement in that particular direction. Accelerometers measure both static and dynamic acceleration. Stepping on the gas pedal when you're driving is a form of positive acceleration, and pressing the brake is negative acceleration. This is an example of dynamic acceleration. Static acceleration is caused by forces like gravity. Static acceleration refers to the force acting on an object when it's not moving or when it's in a state of constant velocity, meaning not speeding up or slowing down. Think of an accelerometer as a device that can feel the way it's being pushed or pulled. They can feel the force of gravity. In space where there's no gravity, these devices are crucial for helping spacecraft figure out which way they're facing and if they're moving. When a ship is in space, the accelerometer senses the direction of the force of gravity, which is usually towards the planet or another celestial body. This helps the spacecraft understand down. When a spacecraft changes its direction or speed, it experiences a force like a push or a pull. The accelerometer can detect these changes by feeling the force acting on it. By constantly sensing these forces, the accelerometer can help the spacecraft figure out if it's staying straight and aligned with its intended direction. If the ship starts tilting or moving off course, it uses this information to make the adjustments to stay on track. Now we're going to use the orientation of an accelerometer to change the tone of a piezo buzzer, because that feels like a way more fun way to make sure my ship is on track. We need an ADXL345 module, a piezo buzzer, and 6 jumper wires, 4 of them male to female. First, we're including a library that provides some functions for this specific accelerometer. We then create an object to reference the sensor called ADXL. All caps ADXL345 is the class, ADXL lowercase is the instance or object of that class, and ADXL345 with parentheses is the communication selection. This means whether we're using SPI or I2C communication. For SPI, you would put the chip select pin in the parentheses, and for I2C, you just leave it blank. Next, we set the range to 2 and the buzzer to pin 9. Range equals 2 is not referring to a pin on the Arduino. The range refers to the range of values that the sensor can measure in acceleration. Accelerometers measure acceleration in terms of gravitational force denoted by G units. 1G is equivalent to the acceleration due to gravity at Earth's surface. When you set the range of an accelerometer, you are setting the minimum and maximum values that it can accurately measure. So setting it to 2G means it can accurately measure accelerations in the range of -2 to +2 along each axis it measures. Choosing a range depends on the expected magnitude of the accelerations you're expecting to measure. Higher values provide a wider measurement range, and lower values provide greater sensitivity. The accepted values are 2, 4, 8, or 16. In the setup, we are turning on the serial monitor and powering on the sensor. We set the function setRange setting to the range that we declared above. We also set the buzzer as an output. In the loop, we're creating integer variables for x, y, and z, which is referring to the 3 axes that the sensor measures. The readAccel function reads the value of the accelerometer. The ampersands in front of x, y, and z is the address of operator in C++. When we use it in front of a variable like this, it provides the memory address where that variable is stored in the computer's memory. This allows the readAccel function to directly modify those values stored at the memory addresses. This way the main code can access the updated accelerometer readings stored in X, Y, and Z after the readExcel function call completes. Next, we print the X, Y, and Z values to the serial monitor. After that, we create an integer variable called frequency and map the X value from the accelerometer reading to a frequency range between 100 and 1000. So negative 1000 will be mapped to 100, 1000 will be mapped to 1000. This frequency value is how we're going to generate a tone with the buzzer to match the accelerometer's x-axis. The tone function takes two arguments, the pin and the frequency. Finally, we'll delay this by 250 milliseconds. Wow, unbearable. Yet another very important project that I'm getting around to way too late in the game, done. I mean, no wonder our ship's not been going anywhere.